Hi guys, good afternoon. And today we are trying to complete the calculations so far. Now we see we have done this 1.5 and we have done reacting masses. Yes, anything to do with mass, how many grams, okay, we have done that already. And also I've taught you how to deduce stoichiometric relationships, okay. Find A, B, C, or X, Y, Z, whatever in the equation. Tricky, but you learn the skills. Today we're going to cover this too. Okay, calculations dealing with volumes of gases, which will involve gas laws. Okay, gas laws. You will do it again later, right? So we will be using, Gale's law and also PV equals to nRT, okay, or equals to mass over mRT. All right. This is the gas law. Second one, of course, is volumes of concentration of solutions. So here's masses, here's gas, and here's solutions. We will look into this later, where we have your number of moles or molarity, right, equals to number of moles over V, or the other form, number of moles equals to mV over 1000 if you want to use it in the m cube, okay? So we look at these things here, right? So we hope I can cover lots of examples, okay? What's some for this, okay? Take the time first, I don't want to miss the boat, okay? Now, let's look at the page, just some theory, okay? Page 38. Right, 37, okay. Now, so far, look at this here, summary. What we have done in calculations is we have learned how to determine MR, okay, of a compound. Remember, MR is the what? Is the relative molecular mass of a compound, okay? We did by spectrometer, remember not, the mass spectrometer, normally, like, let's say this is the spectrum right now. The M is here, it's M over E here, and the longest one is capital M. I told you there's M plus 2, sometimes M plus 4 is here. Later you want this M plus 1, one is M plus 2, we did M plus 2, M plus 4 is here. Okay, so the last line, or the heaviest line, the last value here is the molecular mass normally. The others here are fragments in it. Then we did percentage composition where like for example 35.2% of carbon, 42% of oxygen and so forth. Okay, and so forth. Here you find the empirical formula. Okay, and of course combustion of hydrocarbons we done as well. Your CXHY plus, remember not, your y, x plus y over 2 and HO2 and so forth. Yep. Now these two will be now we're using a lot. Okay. So gas equations where of course this one here to find the MR is PV equals to number of moles. Remember the from the first one here, from the masses here, we have number of moles equals to M over MR. Yeah. So it's N is MS over MR, R and T. So we use it a lot. Okay. Solutions here, we will use, of course, solutions here. Number of moles equals to M, right? MV over 1000. So with the equations you use will be relevant to each one of them. But let's start on gases first. All right. Now, more concepts of gas and solutions. Now we start with this this idea here. This bottom here. Okay. All right. Now remember, you have this is called STP, standard temperature and pressure, which means what is standard temperature? Temperature is equals to 0 degrees centigrade. Pressure is 1 atmosphere. Normally they give 1 atmosphere, or you like in pascals, they normally put 100,000 pascals. Okay, these two are same, right? These two are thing here. Okay, 1 mole of gas. Now I want to show you what it means here. Of course, this one here, this one here. All right, it means RTP. Okay, room temperature and pressure. The temperature of room is taken at 25. I don't care what is in your room. I don't care. Okay, scientifically 25. Pressure is the same. Okay, 1 atmosphere, same as the thing here. All right. So in a gas system, there are 4 variables. You pump any gas into a container. Okay, raw container here. Okay, and you put a piston here to measure the pressure here. The P is the measure pressure here. Okay, so there are 4 things that will determine how a gas are measured. First, the number of moles you pump inside here. Okay, this is the here. Okay, first is N. Number of moles of gas. Okay. Secondly, of course, see the more moles you put here, right? The more it will expand. See, first depends on pressure lah. Pressure, okay, pressure. P for pressure. Small p, big P doesn't matter. And of course, you can say, well, if you pump here, it will register the volume, is it? Right? Volume is measured in many ways, cm cube, dm cube. But what is most important here, we will use meter cube. This is the most important one. Okay? And of course, temperature. The higher temperature, the bigger the volume is it. This all will change. Temperature, normally they give you a centigrade, you will change it to Kelvin, which is plus 273. Okay? Right? Now, that means there are 4 variables. Comes here. 4 variables. You learn in Form 5 saying variables. That means things that can change. And the other things will change. So, pressure, volume, number of moles, and temperature. And so, how do you relate all these 4? How do you relate it? Very simple. Okay, you use P. This is the ideal gas equation. P equals to what? And RT. Okay, R is called the gas constant. Now you can look at the gas constant. You need to know how to look at it. Now this is the gas constant. Okay, this is your data booklet, and you have to know where to look for it. This is the first page. What it means here is for gas. Okay, for gas, right? For 1 mole of gas, right? Okay, to raise the temperature by 1 Kelvin, you need a heat of 8.31 joules. See now. So this is the joules, the energy you need to heat to cause a rise in temperature of 1 Kelvin. Okay, so we'll be using 8.31 here as the standard. Okay, so here we are, right? Okay, now before that, I want to explain this thing here. This thing is asked a lot. Now, this 2 thing here, this is a gas law. Okay, all right. Now it says here 1 mole of okay, I draw it up for you lah. I hope I got a place here. I forgot to put the one. Sorry about this. I forgot to put the here got. Okay. Let's say I've got 4. Let's see here. Okay. Okay. I pump the first gas here, the lightest gas. All these containers same volume. Okay. I make it the same volume. Same. I draw 4 of them. Okay, with the piston here, they show the pressure. Piston here, the lines are a bit crooked because this is they change my what no. They're going to update. I'm going to change this to a new whatever. I don't know. It's not as good as the old one here. Pressure. I'll put 1 more, okay, just to make it more relevant. You can see more examples. You have clearer pictures. Better set the fan first, otherwise you no. Okay, this will be clearer. I forgot to switch on the fan. Now you pump in here the first gas here. Okay, you pump in here 1 mole of hydrogen gas. 1 mole. Okay, so it goes up here. Of course, here, so of course, your gas, right? which is actually how many grams? 2 grams of hydrogen gas. Okay, so let's say the temperature here we keep at 25. Okay, and the pressure, let's say, is like normal pressure, 1 atmosphere. Okay, use atmosphere like easier. Okay, okay, and well, they found that the gas, when you pump one mole or 2 grams, they found that the volume of your occupies is 24 dm3. Fixed one. Okay, right, and this. So I got the moles, I got the pressure, I got the temperature, I got the volume. Now here I pump in a heavier gas. Okay, nitrogen gas. 1 mole of nitrogen gas, N2. 1 mole is 28 grams. 1 mole. Pump. Here. Now, interesting thing is we know that 1 mole of any gas, they would both contain how many molecules? It will contain Avogadro's number there, right? It contains 6.02 and 10 to the power 23 here ppm molecules. And they found that after pumping 1 mole of nitrogen gas, the pressure in 1 atmosphere, it occupies a volume of also 24. If the temperature remains constant, 25. Same thing here if I pump in another gas, okay? Ethene, okay? C2, ethane, C2, okay, and number of moles of C2H6, okay? 12, 20, 12 times 24, 30 grams of, okay? What is 1 mole? Okay, it goes up here, and with the 1 atmosphere, all right, okay, here, the volume is also same, 24. Happen. dm3. Okay, so it doesn't matter what gas is it. I can pump in helium. Number of moles of helium or argon, helium. Okay, 1 mole. They found that the temperature being 25 degrees centigrade, the volume also same. Sorry, 4 dm3. Pressure same. So don't care what gas is it, as long as the number of moles is the same, right? The number of moles is the same, the pressure is the same, the temperature is the same, it will occupy the same volume. Okay? Or I can say the same volume of any gas at the same temperature and pressure will have the same number of moles of gas. That's not. This is how they actually trick you. Make you understand here. See, this came out in your objective before, right? Okay. See, a gas system, the same volume. Same volume. For what we done was what was the volume? 24 dm3 of any gas. I don't care whether it's oxygen or carbon dioxide or nitrogen or C2H6. I don't care. Under the same temperature, the temperature which it was room temperature, and the same pressure. Okay, which we say the pressure equals to 1 atmosphere, is it? Contain the same number of moles of gas, yeah, right? N equals to 1, is it? Okay, this is correct. This is a gas law. Now you can also reverse and say the same number of moles of gas, same number of moles of gas of any gas, right? At the same temperature, 25 centigrade, and the same pressure equals to 1 atmosphere. Contain the same number, occupies the same volume, is it? Which is how much? 24 dm3. Yeah. So here they talk about the variation between the volume and the number of moles. Here they talk about the number of moles and the volumes. Okay. So you must be careful to understand this. Okay, number of moles and volume are related. So we can use this in our combustion of hydrocarbons. See? Okay, Now, you go and think about it. I want to move on, right? How to use this thing now. Okay, now here, not the first one. Okay, I just give these examples. Then after these examples, we will go to our past question. Okay, I think I would. I think I don't know whether I can do it now. No. I want to. Now my it's quite simple here. I just move down here. See the space now. Okay, got space here. Okay, now this question. I don't do here. No blending. Sorry about this. Okay. 0.4 here, 0.400 mass of a gas occupies the volume of 2227 cm cube at 27 degrees centigrade and a pressure of this. Okay, calculate the MR. Now remember, for every question, draw a diagram. I tell you, it's a skill. Draw whatever that can be seen clearly. Like that. I think the pressure got here. So what's the pressure here? The pressure is 100 kilopascals. Remember, you change to pascals, so you change to this. So 100, okay, pascals. Kilo is 1,000. Okay, I hope you know this. And what else? Okay, the mass is equals to of the gas is 0.4. Put on the accuracy here, grams. And what the volume it occupies? 22.7 cm cube. Now change to meter cube. Okay, let's say see to use the 8.31, right? R, it must be pascals, not kilopascals. Must be meter cube for volume. Must be in Kelvin. See now, understand? So you can change all these units. So how to change this one unit is very simple. Now let me show you how to do it. Okay, this is mathematics. I learned it when I was a 4 standard 2 or 5. See, 1 meter cube is equals to 1 meter times 1 meter times 1 meter. This is common sense. Now I also know that 1 meter is equals to 100. Sorry, 1 meter is equals to 100 cm cube. Cm. So 1 meter cube is equals to 100 cm times 100 cm times 100 cm. That's that. Or put down here. Okay, no space. 1 meter cube is equals to 10 to the power of 6 cm cube. That's that. Because 100 times 100 times 100 is 10 to the power of 6. Cm times cm times cm equals see a conversion already. So how to change this to a meter cube? Very simple. Okay, it's not divide. This you divide by 10 to the power of 6. Or you put on the 277 times 10 to the power minus 6 meter cube. Okay, right? You don't know, follow what I do. Skill, perfect practice makes perfect. Okay, now temperature. What's the temperature? Temperature is what? 27. So 27 degrees centigrade plus 273 is equals to 300 Kelvin. Everything is ready. So how to find your MR? Very simple. Use the equation. PV equals to it's nRT, so I change it first. Okay, M equals to MR. Okay, RT. So just by substitution, again, put the MR here first if you like. Mass and R and T over P and V. So you just substitute inside. All right, I won't do it for you. You can do it for yourself later. 0.4 whatever times 8.31 times your 300 over your P. Remember is 100,000 times what is your V? 277 10 to the power minus 6. Okay. The answer is actually MR. I solve it for you. Here is here. Let me see. Okay, page. I did it for you. Now, you can solve for yourself, can't you? All right, it's quite simple. Okay. Solve for yourself. Okay. I just stop it for a while first. I look for it. I'm sure I solved it. I found it. Okay, the answer is here is 43. Okay, 43.93. Right. So very simple, isn't it? Okay. So now next one, of course, next one is a bit different. The density of a gas at 127 degrees centigrade and the pressure of this one is how many grams per dm cube. So no volume is given. So what you do? Very simple. Use your brain a bit. Okay, here's density. Density is mass and volume, is it? So you draw. Okay, I draw first here. No space. Draw it first. I'll draw the thing here. Okay, what's the pressure equals to? The pressure is equals to, given here is 200 kilopascals. So we change it pascals. Okay. Now because the density, this is the density, right? Mass over volume, we can consider this to be one dm cube. Okay, so the volume is 1 dm cube. And the mass, how much? 1 dm cube is 1.70 grams. Cannot, okay? Temperature, you change it to 127 plus 273, okay? Right, now 1 dm cube, change to meter cube. How? Very simple. 1 dm cube is equals to, again, 1 dm times 1 dm times 1 dm. Okay, right? 1 meter, you know, mass equal to 10 dm. So it's equals to, oh, yeah, so stupid. I don't use 1. I use 1 meter, is it? Why not? Okay, never mind. So much go smarter now. Okay, here should be 1 meter cube. 1 meter cube. 1 meter times 1 meter times 1 meter. Okay, now. So 1 meter cube. Okay, 1 meter equals to, so it's 10 dm times 10 dm times 10 dm. Okay, now. So it's equals to what? It's equals to 10 to the power of 3 dm cube. Okay, so 1 meter cube. So to change to meter cube, very simple. Let's rub this one here. All right. Okay. So 1 we divide by the power of 3, is it? So it's 1 times 10 to the power of minus 3 meter cube. Okay. So can solve or not? Can, is it? Right? You apply what? You apply the same equation. What is this? PV equals to M over MR on T. Okay? Substitute inside, you can solve it. Alright? Now next question, I just show you the different type of things with it, okay? Now here, when 0.300 grams of liquid is vaporized in a syringe, now I'm just going to show you a syringe with it. Okay? Now a syringe like this. Okay, in IGCSE, you should be able to see a syringe like that in your lab. Okay, now this is the cork here or the tap here where you push the gas inside here, and then this is called plunger. Okay, it fits nicely inside here, but they draw like that. Okay, so now there are graduation here. Oh, normally it's 100. Okay, 100 cm cube. So you pass the gas here. Okay, I just drop the syringe here. Okay, a diagram is very important. A picture paints 1,000 words, the Chinese say. So as you pump the gas right here, and the plunger move up to here. That's it. Okay. This is called plunger. PLNGR, okay, NGGR, whatever. Here's the what here, okay. So the gas here, okay. Now the gas here, of course, whatever gas here is X2 gas here. So the volume it occupies is right here. The volume, okay. Okay. Okay, huh? So this whole thing is same. You can see it's the same. Just a different way of expressing. I just give all this example so you can see the different kind of things they're expressing. And so next one here. An organic liquid Ri gives the following. Okay, now all is the same, right? Because why? The volume is given in cm cube, so change to meter cube. The mass is given, temperature is given, change to Kelvin, pressure is given, identify what R. Now remember R in the organic chemistry, Rx is your halogen alkane. So R is normally CnH2n plus 1. And then your Cl or X, whatever here. So you have to know R is what is called alkyl group. Okay? Okay? Alright. Okay, so here the idea is all things are given, you can solve it. Okay? So I've given you the 4 examples here. Now let's look at now past questions, how it comes up. Okay? Okay, the first one. Okay, let's go 2, 2, 2, 2, 3. Alright, this is a real thing. Okay. Which mass of gas will occupy a volume of 3 dm cube at 25 degrees centigrade and 1 atmosphere of pressure? 1 mole of gas covers 24 at 25 degrees centigrade. Very simple. Now, if you have a problem, then you draw it out. Okay, draw it. Which is always better. Okay, right? Okay, they say here mass of gas occupies. Okay, 1 atmosphere, so pressure is also 1 atmosphere. Okay, see how they use. Okay, temperature equals to 25. This of course you see is RTP, isn't it? It's RTP, right? Temperature and pressure, RTP conditions. And here, right, the volume here, the volume of the gas is equal to how much? 3 dm cube. Okay, right? You don't know. Now, with all these 3 things, can you find the number of moles? Of course you can find, right now. Okay, now you find the number of moles. But you don't need to find the number of moles in a sense. It's quite simple because, right, see, all right, remember these conditions here, right? 25 cm cube, 1 atmosphere is occupied by 1 mole, and 1 mole has a volume of the same. So you can say, right, 24 dm cube and RTP. What's RTP? Temperature equals to 25. Pressure equals to 1 atmosphere. And occupied by how many moles? Occupied by 1 mole. Therefore, this is very simple way to do all of calculations. So here I got how many, what's the volume here of the gas inside here? So 3 dm cube. At the same RTP occupies how much? 1 over 24 times 3, which is 1 over 8. And it's equals to, by the way, 0.125 moles. So how many grams? So which is this one here? So if you time now, if it's oxygen, it'll be 0.125 times 32. Okay, which is equals to how much? I didn't do it. Did I do it? Did I do it? Wait, okay. Never mind. Let's do it the other way. Okay, 0 here. So find how many moles is this? So for oxygen A is what? 3.2 divided by 32, isn't it? Yeah. How much is that? It's 0.1 moles. Not this one. Okay, nitrogen. 5.6 over 28. Okay. How much is this? 0.2. So not this one here. Next one. SO2. SO2. What's the mass? 8 over. Okay. Over. Now what's the molar mass? Molar mass or molecular mass for sulfur? It's 32 plus 16 times 2, is it? It's how much here? 32. So it's 64. So it's 64. It's equals to, by the way, 0.125. So this answer. Okay. Right. So you just find the number, you convert this to the number of moles. Convert it to the number of moles from where you know the MR is not. Okay. All right, next one, 227. You go back and think over. I'm just going to like rocket speed. Okay. Okay, and this one is a whole big chunk. All right, an organic compound E following compound. Now, of course, here they use the empirical formula. Okay, whatever is it. I solved for you first. Okay, now they found that the empirical formula here, okay, is C3H6. You do it yourself. I don't have to do this. Okay, right? This empirical formula, and it's a molecular formula of 74. Okay, okay, it's on here. I've got no time to do this. Okay, now here, when vaporized in a suitable apparatus, 0.130 grams of E occupies volume, and so forth. Simple. Okay, draw the diagram first. All right, here is your thing. Okay, what's the pressure here? There, 1.00 times 10 to the power of 5 Newton per meter squared. This is the same as Pascal. Okay, now you do your physics, right? Temperature, what? 127 degrees centigrade. Change to Kelvin straight away. 127 plus 273 equals to how much? Normally it's about some 100. Okay, 10 carry 1, 10 400 Kelvin. Okay, right? What else? Volume is given 58.0 cm cube. Change to meter, 58 times 8 times the power minus 6 meter cube. Okay, so they even give you the expression here. So kind of them, I tell you. Okay, so it's MR. So MR, you put MR on top here equals to mass RT over P and V. Easy, is it? What's the mass? 0.130 times what is the RT? 8.31. Look where? From your data booklet times R is 400. So T over what is the P? P you change. You know, you change 1 times 10 to the power of 5 times what is your V? Change V. 58 times 1 to the power minus 6. You found it to be, as I've done here, you found it to be 74.5. Okay, see, about same here. See, 0.5 sometimes it just doesn't matter. So it's same, that means what's the molecular formula? Same as the empirical formula. Okay, right? So here, you can put down there C3H4O, whatever, and calculate out 2. See, now this is the MR, okay? You will get about 74. She said, well, so the molecular formula is this one here. Okay? So this is how you use the gas equations. All right, okay? Now let's look at a bit harder ones now. All right, something to bend your mind a bit. 2, 3, 2. As I said, the more you do, the more you can see that they all come out a bit different. Now this one is a bit different. Quite a hard one, I think. Okay, you can do it. Very good. 0.144 grams of aluminium compound X. It means X is an aluminium compound. You don't know what is it. React with water, excess water, to produce a gas. See, normally it's metal carbide. You know, you learn chemistry. That means like calcium carbide is CaC. You know, at least it's a white color stuff you buy from a shop. To put in water, you get carbide gas. C2H2, okay, acetylene called. Okay, and then with excess water produce a gas, okay, produce a gas. The gas burns completely in oxygen, give you, okay, hydrogen, and that means the gas given out here, okay, the gas given out here is a hydrocarbon, contains carbon and hydrogen, right now, X and Y, because plus oxygen give you what? Carbon dioxide and water. That is the assumption you have to make. Okay? All right? Only, no other things. The volume of CO2 measured at room temperature. This is the volume. Okay. So now what are some things you need to get from here? Okay, I'm going to do up here easier. Okay? So the first thing, of course, is, right? Now put your aluminium stuff first. Aluminium. it should be aluminum, let's say A or X, and carbon Y plus water. Don't care what's not the balance, okay? You give you your, of course, here be your whatever. Normally it's aluminum oxide one. Whatever, okay, don't care, 2, 3, okay. Plus now here is your, you might multiply CX, sorry, should be CY, H, okay, H, Z, let's say, call it. This is not important, but no matter now here, the Y here, the number of moles of here must be the number of moles of here. Or number of atoms here is Y atoms, right? Here the Y atoms. Okay? So this compounds there. Okay? You combine. This is the first thing you need to do. So now this is the first equation. Second equation. Now CY HZ will plus Z and 2 plus oxygen. Don't get excess, they will burn your carbon dioxide and water. If there's Y atoms here, darling, is one is not, okay? It will be Y here is it. That's the assumption you have to make. Okay? So now they say, now the distance from here is volume here is equal to 72 cm cube. I want to find how many moles this is and how many mass this is. Okay, the number of moles, remember it is what? Room temperature and pressure. Okay, run out of steam. Okay. Okay, here. Don't know why this is, so this new is lousy, no? Okay, which means what? RTP. For RTP, 1 mole of any gas occupies 24. So 72 divided by what? 24000. Now it will give me, as I've done already here, just so I don't make any more stupid mistake. Okay, 3 times 10 to the power of minus 3 moles. Okay, of carbon. So I can change the mass. The mass of carbon is equal to how much? 3 times 10 to the power of minus 3 times 12. Why do we do minus something? 0.036 grams, okay, of carbon. That means inside here, the original mass is how much? The original mass is 0.144, yeah? See? So how much, if carbon is 0.036, how many grams of it is aluminum? See now. Now I'm getting it. See ratio, carbon. So mass moles ratio now. Mass moles, see now, ratio. So your mass in grams here, carbon is 0.036 grams. So aluminum would be how much? Would be 0.144 minus 0.036. Okay, carry 1 here is 8. Okay, here's 0, 1, yes, 0. Right? Okay, a mosquito ring around me. So it's 0.108. Change the moles. 0.108 divided by 27 is to 0.036 divided by 12. Look here, it will be 4 times 10 to the power of nice number minus 3. Yes, so it is 3 times 10 to the power minus 3. So what's the ratio? 4:3. So what's the answer? Al4, Cl3. No, it's a different idiot. Okay, Al is on here. Okay. Interesting, isn't it? Right? All to do with volumes. Okay, one more. Okay, all these are quite interesting questions to do with volume. So I want to show you all kinds of now. Please do it again and do it 2 or 3 times until you get the idea. Because you don't know how they're going to come out, my friends. 240. I can finish all this as well and do it a little bit of your. Now here, another one. Another crazy ones. Use the data booklet 15 is relevant to this question. The ratio between aluminum powder and anhydrous barium nitrate is used in a propellant in some fireworks. Came out twice actually. Metal oxides Remember, they tell you because sometimes you don't know the reaction. The metal oxides and nitrogen are the only products. Okay, right? Which means if you want to balance the equation, what happens is this: aluminium plus barium, barium nitrate, very reactive now. Okay, group 2 is it? And O3 bracket 2. You got oxides, the same metal oxides. The two metals here was aluminum oxide and what? And barium oxide, BaO. And plus what? And nitrogen, nothing else, not NO2, no, it's just N2. Okay. Now the thing is here, all right, you are given, okay, which volume of nitrogen. So this is important. Okay, under room conditions, so an RTP is it? RTP produced by when this is of your barium nitrate. That means that this is important. This not important. So the balance equations, I must make sure that this barium, these two are important because I need to know the stoichiometry. The stoichiometry of the equation. Okay, the number of moles here. So here I know that barium, one barium here, one barium here, one barium here. Okay, I'm done. Okay, sorry. One barium here. And nitrogen is 2, isn't it? 2, so here's what 2, isn't it? Balance. So now I can balance the oxygen. So here 2 nitrogen. Okay, now here got one already. I cannot put 2 here. No. I can't put 2 in front here. If I put 2 in front here, I change the barium, isn't it? Cannot. So it must be 1. So it's 1 oxygen here. So the only thing you change, of course, here. So I don't care here already. So now in here, how many oxygen are there? 6 oxygen. Right now. Right? 6 oxygen. So that means that the remainder here must be 5. You know? Here must give me 5 oxygen. Here. So what times should give me 5? 5 over 3. You know. Correct. So 5 over 3, that means here will be how much? 5 over 3 times 2. How much? This 10 over 3 here. I don't care. I don't care about this one here, this number here. I know that 1 mole, right, will give me 1 mole and 1 mole. So, I know what I want. I can get what I want. So to change, if I can find the number of moles of this fella here, I can find the number of moles of this fella here because they're the same. It's not. So this is the number of grams. So what's the MR for barium nitrate? I found out here to make it easier for you and me, man. Okay, it's equals to 261.3. Okay, so the number of moles of barium nitrate. Okay, you go and do don't say I know, then don't do. I'll tell you first, lazy buggers. Okay, what's the mass? 0.783 over what's the MR? Remember, that's why you always have to use all these formulas. N equals to what? Mass over MR, yeah? Always have to use that thing. So it's 261.3. So actually it's equals to, if you count it out here, it's 3 times 10 to the power minus 3. Very nice number of moles. So it's also equals to the number of moles of N2, isn't it? Right? Because 1 mole is 1 mole. 1 mole is 1 mole. Okay? So the number of moles of N2 is equals to 3 times 10 to the power of minus 3. So what is the volume? 1 mole occupies 1 mole of any gas. 1 mole of N2 and RTP occupies how much? 24 dm cubed. So my moles will be equals to 3 times 10 to the power minus 3 times what? 24. Alright? Dm cubed first. So it goes to how much is, you look it up, it is okay, or times 0, 0, 0, like, to make it easy, okay? Right, this is cm cube, isn't it? So answer is 72.0. Voila. Easy, is it? Not easy, is it thing, So you can see they will change the methods, and you have to learn to use stoichiometry. You have to learn to calculate number of moles. You have to learn to see which is important. if they learn to use 1 mole of any gas equal to 24 dm cube, okay, all this jumbled up to give you one beautiful question. This question in your paper 2 is 4 marks. Now here is only 1 bloody mark. Take it or leave it. Okay, the next one. I got only 10 more minutes to go. Okay, I don't think I can do the the solution. Never mind. As long as you know that now do this. Okay, make sure you do it again and again. 261. Okay, I give it different. I went through a lot of work. I tell you, it's not easy. And first, don't appreciate it. Okay, let's make it smaller a bit. Okay, a chemist took 2 dm cube of nitrogen gas measured at the room temperature and react with hydrogen gas. Of course, it's Haber process. Produce ammonia. Only 50% of nitrogen gas was reacted to produce ammonia. How much is what's the mass of ammonia? Now that's okay, very simple. Okay, of course simple to me or to you, but I hope it's simple. So, and to give equation first. Okay, if you know the equation, better still H eraser. Okay, this eraser is better than the old one. H2. Okay, 1 arrow enough. 2 and H3. So 1 mole is to 3 moles is to 2 moles. Stoichiometry. Okay now. So here they say, well, he took volume here 2 dm cube. Okay, right? This excess. How do you access? They tell you a large volume. Okay. All right. So here only 15% of this is reacted, isn't it? Yeah. Yes. So wait, first you can convert this to moles first. So remember, I'm going to do here, right? 24 dm cube of N2 at RTP. Why RTP? Why RTP? And RTP. All right, occupied by 1 mole. So 2 dm cube. How many moles? Very simple. 2 over 24. Okay, is actually equals to 1 over 12 is actually equals to 0.08333, whatever the continuum. Okay, right now. And out of this, how many percent is reacted? Only 50%, right? The rest are all lost. 50%. And how many is this? And how many is this? I calculated out. Okay, is equals to 0.0125 moles. Okay, so 0.0125 moles, which is reacted, will react with how much? 3 times 0.0125 moles. To give how much? How many moles? 2 times 0.0125 moles. Which will give how many moles? Which will give you 0.025 moles of ammonia. So they ask you how many grams in, right? So N equals to mass over MR. Yeah. So what's the MR for ammonia? 14 plus 3, 17. So mass is equals to 0.025 times 17 equals how much? If you do it up by itself, it's equals to 0.425. 0.425 grams, which is, my friends, so. Okay, take it for a while and learn to see this. Okay, I got 3 more questions to go. Okay, let's hurry up a bit. Okay, next one. 287 now. Okay. This is a bit tricky one. A flask of volume 100 cm cube was first weighed with air filling the flask, and then another gas Y. The results measured at 26 degrees centigrade for 1 atmosphere there given is shown. Okay, now remember here, they both contain the same apparatus, okay, right? The mass of the container, let's say, is put A like A grams. A grams. So the air, okay. All right. So the point is the mass of the container air density here. Okay. Now can I find what means the flask the flask, okay, plus the air. Can I find the mass of air? No, of course I can. Density equals to what? Mass over volume, right? The volume is equal to how much? This one here. So what's the density of the air? 0.00118 grams, okay? So it's mass over cm cube, okay? So I use the cm cube per 100, okay? So the mass of air is equals to, if I were to get out, is 0. Okay, so remember, times, isn't it? So 0.118 grams. Okay, right. So if I minus this from this one here, if I minus 47.930 minus 0.118 grams, I will get the mass of the flask. Mass of flask. Okay, which is how much is the mass of flask? Okay, minus that. Well, let me see. I make it easier for me. 47. You can check it out. 812 grams. All right. So of course now I can minus from here to get my mass of Y, can't I? Right. So it's 47.989 minus 47.812, which will give me. Okay, which will give me what mass is it? Yeah, let's see quickly. 49.93. Okay, 0.177 grams. Okay, so 0.177 grams here. Okay, and in the volume of the volume here is equals to 100 cm cube. Temperature and pressure here. Temperature here is equals to 26 plus 273 equals to how much? 992 Kelvin. Volume is how much? 100 times 10 to the power of minus 6. Pressure is equal to this one same. Pressure is equals to, okay, this is the, okay, pascals. So I can use my, put down guys. Okay, I can use now P V equals to M over MR RT. Okay, so MV here equals to, what's the mass? Mass of Y here, 0.177 times 8.31 times temperature of 299 over, what's the pressure? Pressure here is it? 1 times 10 to the power of 5 times the V, volume is given there, 100 times 10 to the power of minus 6. Okay, if you work it out by yourself later, I'm sure you will. Is about 43.98. Isn't it? Okay, so you can see the different ways they are being asked. I got about 5 to 10 more minutes. Okay, quickly. I think I'll do one more, that's all. That one is quite simple one. Oh, not so simple, maybe. Okay, now I do it. 262. Okay, here we are. So here, organic chemistry. In the experiment, 12.0 dmK of oxygen measured under room temperature is burned with 0.1 mole of propanol. Now, propan-1-ol is actually, so this one, CH3, CH2, CH2, and OH plus oxygen. You need to know the equation, okay now? Give carbon dioxide, okay? Completely, that means no carbon monoxide, no carbon, only carbon dioxide and water. Balance equation, 3 carbons here, so it's 3 here. Okay, how many hydrogens here? 3, 5, 8, so it's 4 here. Now you must balance the oxygen. Here's 4 plus 5, 8, isn't it? 4 oxygen here plus 6, sorry, 6 oxygen here. I say 5, gundu, is it? 6, 10. So now here got how many? Here got 1, okay, so to make 10, here must be 9, isn't it? So it's 9 over 4, 9 over 2, it's not, or 4 and a half. Okay, so one more must react with 4.5 moles to give you 3 moles, to give you 4 moles here. And this is the mole ratio. So now it says here in experiment 12, here the volume is how much? 12 dm cube. to burn. Here the number of moles is given 0.1 mole. Okay, now change it to moles. Divide by what? As a room temperature, is it? Yeah. So divide by 24 is equals to 0.5. These are moles. So 1 mole requires 4.5 moles to form 3 moles. They ask you what's the final volume of gas. It means the gas will be your carbon dioxide. Water don't have anything because it's liquid already, plus any excess oxygen behind, excess, unburnt. So 1 mole react with 4.5 moles, 0.1 mole react with how many moles? 0.45 moles reacted. So how many moles unreacted? Unreacted of oxygen moles equals to 0.5 minus 0.45, 0.05 moles. Here again, how many moles? 1 mole give you 3 moles, 0.1 mole give you 0.3 moles. So the total of 0.3 plus 0.05. How many moles of gas? 0.35 moles. Okay, right? Then what's the volume? Okay, times what? Times 24. Yes. Okay, so times 24, how much is it? It's equals to 8.4 dm cube. I've done all my work already. Which is what? 8.4. Okay, go ahead and try it. Now, one last question. Okay, I think I can finish this. So that you have more experience. Okay, I can't do the solutions. I thought I can do 3, 4, 3. Okay. Look at here. This is a very good question. It's different because all the things Cambridge is not going to be stupid and give you some easy ones. It's different, but it's simple enough. Okay, number 3, the compound S2O7. You heard of it? You haven't even heard of it. Okay, it's hydrolyzed in water. It means that plus water. Okay, S2O7. Okay, plus water. It means water becomes a reagent, friend. You learn this later. To give you sulfuric acid, H2S4, you need NOAH, plus what? Oxygen only. 2 things, right? Right? Which volume of oxygen measured at room temperature and pressure is evolved? Find here. What is the volume given out? When here the mass given is how much? 0.352 grams. Okay, it's hydrolyzed. Now, first of all, you have to balance the equation. 1 mole here, so 1 mole here. 2 sulfur, put 2 in front here. 2, right? 2 here. Now hydrogen is 4, so put 2 here. Now see whether the rest are balanced. Here 1 mole here is 7 oxygen. Here's 2 oxygen. So now oxygen, right? Here is 2 and 4, 8 is it? So put half here. Is it? See, run out of thing already. I don't know why. Okay, never mind. Okay, 2. Okay, half. Easy, isn't it? So convert this to number of moles. Easy, isn't it? Always 0.352. Okay. Now what's the MR for this one here? MR. I worked it out already. You can do it yourself. Just to make it easier for us. 176 divided by 176. Okay. Right. It's equals to actually 2 times 10 to the power minus 3. So remember here 1 mole. Right, with 2 moles. Give 2 moles, here half a mole, 0.5 moles here. So 1 mole give you 0.5 moles here. So remember 1 mole is to 0.5 moles. So it's S2O7, this O2. Okay? Right? So 2 times 10 to the power of minus 3, here's how much? It'll be 2 times 10 to the power of minus 3 over 2. So 1 times 10 to the power of minus 3. Yes? Minus 3 here. So, what is the volume at RTP, room temperature, times what? Times 24. Here is cm cube. Okay? So, 3, this 3 here, so go 1, 2, 3. So, it's 24 cm cube. Voila! Whew. Okay, guys, I finished. So, I've done with you to find MR for solids I'm done with you to find MR for gases in various type of conditions. The next one we'll do is to find the MR or how to calculate from solutions, okay? Which is the hardest, not the hardest one, the most popularly used one for practicals as well as for theory-wise, okay? Please do again and again, get yourself, don't just say, I can do, You cannot do that. You do again, close the book and do again and get the right answer. And then do again. Do 3 or 4 times until you get it right. Okay? Okay, goodbye and all the best.